Okay, so in this next video, we're going to be talking about descriptive statistics. For this, what we're going to be doing is we're first going to be going over what descriptive statistics are, why they're important. Then we'll talk a little bit about what you need to look at. And then finally, we'll be discussing how we can use our descriptive statistics and some basic data visualization of descriptive statistics. Okay, so first, what are descriptive statistics? Broadly, what they are is that they are simple summaries about the sample that we've collected. And this can include a number of different things that can be quantitative in nature. So, for instance, things like the mean, the standard deviation, the median, the variance range, interquartile range, um, modality, that is what is the most common number that occurs within the data set, as well as the skew, which is how much the data set may shift to one side or the other, and then the kurtosis, or how clustered the data are as well. These data can also be visual. So for instance, we can look at the skew of data visually, the kurtosis of data visually. We can also look at these things through things like histograms, box plots, and things of that nature. In terms of how statistics work broadly, I'll be coming back to this in a later video as well. Broadly, statistics are classified into one of two broad domains. First, descriptive statistics, as I just mentioned, but then also inferential statistics. However, while we know that descriptive statistics may not be the most interesting thing to look at, they are necessary in order for us to make inferences about our data. So when we do any sort of biostatistics, we're really interested in trying to understand like differences between groups, or how one variable may be related to another variable, but that requires that we understand what our data look like first before we can actually make any decisions about what we should be looking at. And so that's why it's a very important key concept that we know and understand what our data are. If we don't know what our data are, we're not going to be able to make anything be possible in terms of doing any inferential statistics. And this is because inferential statistics are based on some basic assumptions that we'll talk about a little bit later in a future video. So if you don't meet those basic assumptions, then your conclusions about your data may actually be false. And it's important that we meet those assumptions first before we do any sort of analysis. And then it's also important that we recognize that our data may be influenced by the skew, the kurtosis, the variance in the data, and then also the distribution of the data themselves. So here's broadly what we would expect our data to look like overall. And I'm sure most of us have seen this basic bell graph at some point, wherein we see that nice, pretty curve to the data set. And broadly, we would think that the midpoint of the data would be the mean, and then one standard deviation out from the mean, that would be getting about 68% of our data. Two standard deviations out, we'd be getting about 95% of our data. And then three standard deviations out in either direction, we would be encapsulating about 99.7% of our data. And just as a reminder, the variance of the data is how much it varies from the mean on each individual number, and that is then squared and divided by the number of participants in the data. And then the standard deviation is just the square root of that. So in terms of what we would be looking at in terms of our basic modalities our basic distributions of the data, it's not always going to be that nice bell graph. It would be great if it were, but oftentimes it may not be. Sometimes we'll be looking at unimodal data. Sometimes we'll be looking at bimodal, that is two different humps occurring in the data, or two different curves. We might be looking at multimodal data, that is more than two curves that occur in the data. And then it's also important to note that while it may be the dream for us to have the distribution of that really nice, pretty bell curve, wherein the mean, the median, and the mode are all directly symmetrical, standing right over the center of the bell curve, in reality, that's not going to be the case. What we may oftentimes see is we may see that the median is going to be slightly less than the mean. That would indicate some positive skew. And then we might see some negative skew as well, wherein the median is going to be slightly greater than the mean. And this will really be dependent upon the variable that we're looking at in interest. So with this being said, what we also might want to look at as well are things like histograms and probability plots, as this is going to tell us a lot about the distribution of our data. And so up on the top, you can see a histogram showing the frequency of distribution at different amounts of sales price. And then underneath, we can see the probability plot for some variable of interest. And what we can see here is that at the very tail ends of the distribution, we can see that some values are quite a bit further away from what we would expect for those variables of interest. So in summary, what you need to do is you need to get to know your data. And it's really important that we use descriptive statistics in order to understand what our data looks like so that we can make inferences about our data. And at a very minimum, we should have an idea about the means, the standard deviations, and the shape of our data set. Okay, so with that being said, let's just go ahead and we're going to do some basic descriptive statistics in R. So with this in mind, let's go ahead and let's open our copy of RStudio again. And we're just going to go ahead and we're going to load our data set. And this time, just like before, we can do this just using that pacman function that we might have talked about a little bit earlier. But again, you would just have to load that function using this command here at the top. And then underneath, this command is going to load all the individual packages that we're interested in using for our data set. So once again, we're going to go ahead and we're going to set the working directory. If you don't know where your data are located, then what we can do is we can just go to where those data are located. And I'm using a Mac, obviously, but what I'm trying to do is I'm trying to just get the path name. Once I get the path name, I can go ahead and I can enter that in this command here. And you might have to do a little bit of changing up. This little squiggly line will help to allow the set working directory command to work correctly. And then from here, if we just want to check, make sure we're in the right area, then obviously it is, just based off of that set working directory command. Okay, so from here, let's just go ahead and let's just load those data. Once again, and I'll just make this nice and big so that way we can all see what I'm talking about. And then once we've loaded our test data, then let's just go ahead and we're just going to, for simplicity and ease, we're just going to rename a bunch of variables here just to make it easier for us to review these data in particular. So once we run that command, then we should be able to get everything to run. Now, if you see this, that just means that there might be an issue with having our data, the DPLYR package loaded. So just go ahead and make sure that's not loaded. And then we can go ahead and we should see that our data look very nice and there's some nice easy names for us to use. So for these this data set, I'd like to just briefly go over what each variable represents. So we have some sort of intervention that has 3 time points. These are all practice data. They are not real data, so please don't read anything into it when you're doing the practice set. Once we have this group intervention and control group, we have an age group, we have an age variable or variable representing sex or biological sex. We have a variable representing education, height, weight, body mass index, and then this variable representing cognitive performance on something called the ADAS cog. Higher scores indicate poorer cognitive performance on this variable in particular. And then we have something called the 6-minute walk test over here. So the 6-minute walk test is a measure of physical function, and higher scores on that indicate somebody has better physical function, meaning that they walked further over the course of 6 minutes. Okay, so once we have our data loaded, let's just go ahead and we're going to start doing some very basic statistics with this. So let's just start looking at what somebody's age is in the data set. So we can do this using the describe command. So we'll use describe, and then let's just go ahead and let's look at those data from baseline. So the easiest way to do this is to just create a new data set where you're just going to be looking at baseline data. And to do that, we would just use the subset command, and then we would go ahead and we would go to time equals 1, and we have this new data set composed of just individuals at time point 1. So from here, we're just going to go ahead and we're just going to describe age at baseline. And so we would just use describe and then in parentheses baseline age. And from here, this is going to provide us with a good number of data here. We'll be able to see we have info about the mean, grand mean difference, and what variables exist at the 0.5 percentile all the way to the 95th percentile. Now this in particular doesn't necessarily provide us with the best information that we might have. So in order to make sure that we have the best possible information, what we would want to do is we would actually want to use a little bit more of a we would want to make sure that our ability to actually view these data might be a little bit more clear. And so there's a couple different ways that we can do this. Usually the psych package is something that works quite well for this, but as you can see, it's we're still having some issues in terms of describing these data. But we can also look at things like the mean. We can also just directly call the standard deviation, or things of that nature. Now, we might also be interested in using the describe by function. And this might give us a little bit of a cleaner look at these data in this case. And so in this instance, we're able to see a little bit more information about the mean. As we saw before, it's the same mean, standard deviation, the median, the range from min to max, and then also the range, the skew, and the kurtosis as well. Now we can also look at differences as well in terms of getting a 5-number summary using the baseline age command, and that's going to give us that min, the first quartile, median, mean, third quartile, and the max. Now we could also, if we were interested, we could look at everything together for all variables, and we can do that using the describe by command, and we just would put in baseline. And there we go, we have a summary for all the variables included in this data set. But if we were also interested as well, is we could get a nice visualization of what the distribution of the variable age looks like. And that can be done using basic histogram. So you would use the command hist and then parentheses baseline age. And then that's going to go ahead and create a histogram for us right over here, as we can see. And we can see that there's a decent amount of kurtosis, especially around the ages of 70 to 80 years old, at least in these data. Okay, so we can also go ahead and use the describe by function as well to be able to look at group differences. So we can use describe by again, but this time we're going to go baseline age and then comma baseline group. And what that's going to do is that's going to give us group differences in terms of means and standard deviations between the intervention group and that control group. Now let's say I have a variable that's not a that's a proportional variable or a categorical variable. So for instance, let's just go ahead and let's look at sex differences between, or group differences as well, both of which are categorical in nature. So I can use the function table, and then from table baseline and group. And that's just going to tell me that there's 20 individuals in the control group, 20 individuals in the intervention group. I can do the same thing if I were so inclined for looking at sex as well. And again, that's that 0-1 variable. So we have 26 zeros and 14 ones. Now in this case, I'm assuming that males are 1 and females are 0, but that's just based on however you might have coded the data. Okay, so next up, we can also use that proportional variable as well to be able to look at group differences in terms of proportion. So we haven't looked yet at whether there's differences between groups in biological sex, for instance. So in this instance, we can go ahead and we could just go ahead and make another table, but this time I'll just put baseline of sex and baseline of group. And now I can see that there are 11 zeros in the control group, 9 ones in the control group, and 15 zeros in the intervention group, and 5 in the control. But I could also, if I wanted to, I could look at this as a proportional table as well. So I could look at the proportions in terms of the number of people included in each group. And so to do that, I'm just going to set this up the same. So baseline, and then group. And then I'm just going to use this margin equals 2 call. And that's just going to give me the proportions for what I want in terms of the number of people from each group. So from here, 55% of the control group is 0, 45% is 1, 75% of the intervention group is 0, 25% is 1. Okay, now there's also another way that we can use these data as well, is we can also try to look at another different thing where we would make certain data categorical in nature. So right now these are all numbers for the most part with the exception of group. So let's just go ahead and let's try this again, but this time we're going to go ahead and we're going to create a new variable for sex, wherein we're creating sex into a categorical variable of male and female. So again, 1 is male, 0 is female. And so now if you were to look at these data, I can see that I now have them listed as male, female. Okay, and so if I wanted, now what I can do is I can create this new table using something called table 1, which is a nice easy way of being able to look at differences between groups using a really neat package called table 1. And so if you haven't already loaded it up here, then go ahead and try loading it using the library table 1 command if it's not already loaded on your version of R. And so what we can do is we can actually make a neat little table wherein we're going to first use the call names function. So call names of baseline. And so we have each of these individual variables of interest that we have. And then let's just make sure we're using the most up-to-date version. So I have been using data 1. Let's just go ahead and let's use data 2. And so again, that's going to give me the nicer versions of every name of the variables. And so from here, I'm just going to go ahead and rerun that. And then I'm going to call the individual variable names that I want to make a table for. So in this case, I'm going to just create some variables that I want to include that are numerical in nature. So in this case, let's just go ahead. We're going to include age, which is column number 4. And you can do that just by counting 1, 2, 3, 4. And then let's just do one more for ADAS-Cog or for BMI, ADAS-Cog, and then meters walk. So that would be 9, 10, and 11. So we have this new vars name called D output. And sorry, I didn't have enough parentheses there. Oh, now I had too many. Maybe not enough. Hang on, we got to count this out. Okay, so we've got 1, 2, and then 1, 2. Okay, so we're having a little bit of trouble here with this. Just give me 1 second while I get this set up. So fortunately I do have the command written in. And so this is why it's important to save your code if you don't already. And so of course I'm forgetting one thing here. So as you can see, just go ahead and use this one right here, and then we're just going to use the same numbers that I had before. So 4, 9, 10, and 11. And now as you can see, it works just fine. Okay, and then we're going to separately call the categorical variables of interest that we have. And so for instance, in this case, the categorical variable that I'm interested in is going to be sex. So I've got 1, 2, 3, 4, 5. So let's just go ahead and let's just call sex cat vars. And so then what you can do is you can use this function of table1, create one table 1, and then if you call the vars listed in this function right here, and you can see over here it's just a list of values with the names of the variables that you're interested in, and then you can stratify it by group, and then all this will do is it'll make a nice little table for you between groups. And I can do the exact same thing as well for my categorical variables if I'm so inclined. So let's just do the same thing. And again, I'm creating table 1 using just the categorical variables. And all this will do is it will show the number of males in my control group and the number of males in my intervention group. And then if you're interested in doing baseline differences, which you shouldn't do if you're doing a randomized control trial, but if you are interested in looking at baseline differences, then you also get a p-value for looking at baseline differences between groups. And so that's it in terms of our descriptive statistics for right now. So thus far, we've gone through how to make some basic histograms. We've talked about doing some basic descriptives in terms of the mean, the standard deviation. We can look at the median, the 5-number summary, and things of that nature. And then we also went over a little bit about how we can use table 1. In the next video, we'll go through the practice problem data set and discuss how we can answer each of those problems that I gave you.